All right, today we're going to pull back the curtain on the hidden world of software security. And what we're about to find, well, it might just surprise you.
You know, we put an incredible amount of trust in programs to keep our digital world running safely. But what happens when the very watchdogs designed to find flaws are themselves flawed? It's that classic question, right? Who watches the watchman? Except this is for the digital age, and it's a question that, believe it or not, affects every single one of us.
So here's our game plan. We're going to journey from a hidden danger in our digital defenses to a really clever new tool that's making things safer. We'll see how it works, what it found, and, most importantly, why all of this really matters.
So who exactly are these master detectives of the software world? Well, they're not people. They are incredibly sophisticated programs that act like the invisible building inspectors for our entire digital world.
They're called SMT solvers. Yeah, it's a mouthful. It stands for Satisfiability Modulo Theories. But you can just think of an SMT solver as this brilliant, super-fast logician. It looks at the very blueprint of a program and asks one simple question. Does this logic actually make sense? If it holds up, the formula is satisfiable. If it's a total contradiction, it's unsatisfiable. Simple as that.
And what's really wild is just how essential these solvers are. I mean, this isn't some obscure tool used in a university lab. No way. They are the absolute bedrock for huge companies like Amazon securing their cloud services, and they power other critical tools that automatically test the software you and I use every single day.
So this brings us to that huge classic paradox. How in the world do you check the checker? If the very programs designed to find bugs have their own bugs, how would you even know? It's a really serious problem. So the older testing methods, like a tool called Storm, were pretty clever. What they do is ask a solver for just one possible solution to a complex logic puzzle. Then, as you can see here, they'd break that big puzzle down into smaller pieces. And finally, they'd use that one solution they got as a kind of map to reassemble the pieces into brand new puzzles, creating tests where they already knew the answer.
But, and this is a huge but, there's a massive problem with that approach. Relying on just one single solution is like trying to understand a complex sculpture by only looking at it from one spot. You're just guaranteed to miss things. You've created a giant blind spot for yourself. And this right here illustrates the issue perfectly. Look at the left side. Based on one solution, a piece of the puzzle might look totally false. So the testing tool just throws it away, ignores it. But check out the right side. A different, perfectly valid solution could make that exact same piece true. And that piece that got ignored, it might have been the one and only key to finding a hidden bug in the solver itself.
Okay, so how do you get around these massive blind spots? How do you see that sculpture from every single angle? Well, that's where a new, much more thorough tool comes into play.
It's called Octopus, and its name is honestly perfect. Okay, get ready for the full name. Oracle Guided Testing through Synthesizing Inputs with Multiple Assignments. Don't worry about memorizing that. The key idea is right there in the name. It's designed to work like an octopus, using many different arms to explore tons of logical paths all at the same time.
So how does this whole multi-armed approach actually work? How does it manage to find the bugs that other tools are literally blind to?
Octopus has this brilliant three-part strategy. First, and this is the most important part, it gets multiple solutions for the same puzzle. This lets it see the logic from all sorts of different angles. Second, it generates brand new puzzle pieces, or snippets, from scratch to mix things up. And third, in a really clever twist, it creates puzzles that are guaranteed to be unsolvable.
And that second point is a total game changer. You can see it right here on the slide. Octopus isn't just recycling the original puzzle pieces. Nope, it's actively creating brand new synthetic bits of logic. It's like it's inventing new words for a language, which lets it build way more diverse and much more challenging tests.
This brings us to that third strategy, which is just a huge innovation. When a puzzle is impossible, Octopus can find what's called the unsatisfiable core. Just think of it like the one broken piece on a game board that makes the entire game impossible to win. It then uses that broken piece to build new tests that should fail. It's an amazing way to check if a solver gets cocky and claims it's solved an impossible problem.
Okay, so this all sounds fantastic in theory, but did it actually work? Did this new multi-pronged attack actually find anything wrong with these super important SMT solvers? The answer is a resounding yes.
13.
Octopus found 13 previously unknown bugs in some of the most advanced, widely used SMT solvers on the planet. That's 13 potential cracks in the very foundation meant to keep our software safe.
And take a look at this table. These weren't just minor glitches in some obscure programs. They were found in industry-leading solvers like Z3 and CVC5. The developers confirmed 11 of them, and as you can see from that fix column, they've already patched up the vast majority. This had a real impact.
Now, most of these were what's called a soundness bug. And let me tell you, this is the absolute worst, most dangerous kind of flaw a solver can have. It is the digital equivalent of your calculator confidently telling you that 2 + 2 = 5. It doesn't just crash or give an error, it gives you the wrong answer and insists that it's right. It completely breaks the trust you have in the tool.
And get this, one of the most critical bugs found in the CVC5 solver could only be triggered by one of those impossible, unsolvable puzzles we just talked about. This is the perfect proof of Octopus's unique power. It found a bug that the old methods were structurally incapable of ever finding. So let's just zoom out for a second. We're talking about bugs in a super technical tool you've probably never used directly. Why does any of this matter to you and me?
Well, it's pretty simple, actually. Stronger, more accurate solvers directly lead to more reliable and more secure software for every single one of us. By finding and helping to fix these deep foundational bugs, tools like Octopus are making the entire digital world we all live on just a little bit safer.
This story of Octopus is this powerful reminder that the hunt for bugs is a truly never-ending cycle. It proves that even the tools we build to check our other tools need checking themselves. And that leaves us with a pretty big question, doesn't it? In a world built on code, what other untestable foundations are we all just silently taking for granted?